So, welcome everyone to this meeting of our seminar series. It's a big pleasure for me to introduce Lydia Patton. Our speaker today is from Virginia Tech, and she will talk about third generation gravitational wave astronomy. Thanks again, Lydia, for being here with us.
Oh, excellent. Thank you so much. And I really appreciate having this opportunity to speak and to come into contact with the Cosmos Project. I think this is just such a wonderful project and group of people, and I'm very glad to be part of it. And today, I wanted to talk about the third generation detectors, third generation gravitational wave astronomy. And so before I get into the actual talk, of course, I don't think I have to say much for everyone here, but just to say what third generation means. Of course, there were the first generation of detectors that were built. And then there's what's often called the next generation. So the next generation Event Horizon, Advanced LIGO, and so forth. And then now there's a third generation of telescopes and detectors, interferometers that I'll be talking about. So there's one more thing that I wanted to talk about just briefly before getting into the actual talk, which is that, of course, I'm going to be talking about what in some ways is an ideal future for these instruments. Many of the instruments that I'm going to talk about today are planned and funded, but may or may not. Hopefully they will all come to fruition. And so I'll talk about what the plans are for them. Okay, so what I'm going to talk about today is the next generation of detectors in gravitational wave astronomy. So what's planned and what's going to come online soon. Um, and I'm going to talk about a couple of particular topics that I find of interest. There's a really broad range of topics that we can talk about in terms of the next 10 or 20 years in gravitational wave astronomy. And but for this talk, I want to focus on the search for dark energy, on tidal events and distinguishing contributions of different stellar and black hole sources, and on the interesting phenomenon of multibanding, which we'll talk about towards the end, which has to do with the combination of detectors in instrumentation and in methodology. So I'm going to talk about some specific topics. I'm not going to be making an overall philosophical argument except the following, which is that when we talk about detectors, often we talk about increased sensitivity, increased detector sensitivity, so that scientists will be able, astronomers and others will be able to find, to detect events and phenomena and stars and black holes at lower and higher frequencies and bandwidths and ranges. And often detector sensitivity is spoken of as kind of the main or preeminent step forward when there's a new instrument that comes online. And one thing that I really want to emphasize today is that for many of the most exciting things that are happening in the third wave of gravitational wave astronomy, there's a kind of blend of detector sensitivity, modeling, and simulation. So in a sense, like sensitivity comes along with various types of inference and modeling, and even what might be called theoretical reasoning, so that in fact the sensitivity is just one component of the advance that the next generation brings. So this is something that I want to really emphasize, and it'll come up pretty much in everything that I talk about. So I'm not going to try to, hammer that point home too much, but I'll just mention it each time. I'll mention how, detector sensitivity is, of course, incredibly important, and it's exciting, but it, in fact, is much more exciting as part of this larger context. Okay, so I want to start by talking about the next generation of detectors. So again, I've mentioned that Research into black holes and neutron stars and other stellar phenomena is being carried out already by large-scale research projects using interferometry. So these are, as is well known, the LIGO Virgo Kagra or LVK, and radio astronomy by the Event Horizon Telescope. We are already in the era of advanced LIGO and the next generation Event Horizon Telescope, which is planning for, sort of second generation or advanced detection. But then there's a third generation, what's already become known as the third generation set of detectors. So one of these is, of course, the space-based observatory LISA, but there are also a number of ground-based detectors that are planned to come online in the 2030s. So these include the Einstein Telescope and the Cosmic Explorer. And these detectors are planned to increase the sensitivity of gravitational wave observations many times over LIGO and Virgo. And here, of course, I'm using observation in a broad sense. The next generation of the Event Horizon Telescope, which is, of course, a project that turns the Earth into a radio telescope, will substantially increase sensitivity by adding many more radio telescopes to the project. So up to 2017, the project included 8 telescopes, including Atacama, the Submillimeter Telescope in Arizona, the James Clerk Maxwell Telescope in Hawaii, and the South Pole Telescope. And between 2018 and 2020, 3 more telescopes already came online, including Kitt Peak, the Noema Telescope in the Alps, and the Greenland Telescope. And there are a number of telescopes that are already planned, and Yulia Strobashevsky, who's here, can tell us that are already planned for the next several years to come online with the Event Horizon Telescope. And of course, each new telescope provides new sort of second degrees of arc, right, in the resolution of the Event Horizon Telescope. So in the realm of third generation interferometry, the Einstein Telescope in the States is accompanied by a great deal of excitement. So here's one of the statements of the importance of sensitivity. So Hild et al. Wrote about this in 2018. The ambitious goal of the Einstein Telescope project is to provide a conceptual design of a detector with 100 times better sensitivity than those currently operating, which corresponds to a capability of scanning a 1 million times larger volume of the universe. And it's expected that this will require the development and implementation of new technologies, and that these go beyond the concepts employed for the first and second generations, especially the reduction of quantum noise. So here already, even though the emphasis here is on detector sensitivity and on the ability to scan more of the universe, it's also the case that there are coming along with detector sensitivity, even if you're just looking at instrumentation, you're already going to need additional noise reduction. You're already going to need additional methods to deal with new problems that come up when you have increased detector sensitivity. So this isn't the only point that I'm going to make about that, but it's one important point. So this is kind of the one of the main points that I want to make, other than just that there are some really interesting things about the third generation of gravitational wave astronomy that I want to emphasize. The main point I want to make is increased detector sensitivity alone doesn't necessarily put us in a better epistemic position to learn about the phenomena of interest. Sensitivity, of course, goes along with other even methods to do with instrumentation or instrument readings, like noise reduction and instrument modeling. But additionally, there are advances in the models of the phenomena, in computer modeling, in simulation methods, and in our understanding and mapping and cataloging of the phenomena that are going to also be of incredible importance in bringing the third generation online. So first I'll talk about the Einstein telescope, which, all going well, will come online sometime in the next 20 years. Hopefully 10 years. The Einstein telescope will make it possible for the first time to explore the universe along the cosmic history of the universe from the cosmological dark ages. Of course, this is kind of a press release. This is from their website, so they're saying this in a very kind of like it's an ad. It will probe the physics near black hole horizons, help us understand the nature of dark matter, which we'll talk about in a moment, including primordial black holes and axion clouds. We're going to talk about axion clouds right towards the end, and dark matter accretion, and the nature of dark energy and possible modifications of GR at cosmological scales. So there will be this new Einstein telescope sensitivity and exploiting a new frequency band, especially larger mass objects. The entire population of stellar and intermediate mass black holes will be accessible over the entire history of the universe. And that's, of course, incredibly exciting for astronomy. We're going to have new access to origin, evolution, and demography of stellar populations. One of the important points here is that the Einstein telescope is going to focus in particular on the in-spiral phase of neutron star mergers and looking at tidal effects. And again, we're going to talk about tidal effects later on towards the end of the talk. So one important point is that towards the end here, you see that the Einstein telescope is going to operate with a new innovative generation of electromagnetic observatories. And that becomes, in fact, incredibly important for the search for dark matter and dark energy, as we'll see in a moment. Okay, so this is a similar kind of press release sort of website for the Cosmic Explorer. We're going to go through this fairly quickly because, of course, this is just something you can see on the website, but I wanted to make sure we had kind of a grounding of like what's going on with these new detectors. So Cosmic Explorer is going to be able to detect merging stellar mass black holes at larger redshifts. There's going to be a larger reach. This is going to be, if Cosmic Explorer comes online as planned, and at the sensitivity that's planned, it will reveal, this is a quote from the website, for the first time, the complete population of stellar mass black holes. And this will give us a lot of really interesting information, including the black hole merger rate and the underlying star formation rate. And this is incredibly important for cosmology. It's also true that Cosmic Explorer is going to be looking at neutron star matter and looking at the pressures and densities found in the interior of a neutron star. We'll talk in a moment about some of the reasons that that's interesting and important. One of the main reasons is going to be that for a lot of the most exciting phenomena that the new detectors are going to be investigating, what's really important is being able to discriminate between what's contributing to what effect, right? So if you have like a neutron star disturbing the tidal, creating tidal events around a black hole, for instance, then you need to be able to tell like what's being contributed by the neutron star and what's being contributed by the black hole. And we're going to talk about that in a minute. And Cosmic Explorer, then the on the right here, we just have this sort of, when you build a new detector, you might get unexpected things. We might see the core collapse of a massive star or emissions from mountains or quakes and pulsars and glitches in magnetars, et cetera. And so there's these kind of exciting potential phenomena, potential detections that people are speculating about that might come from the Cosmic Explorer. So this is also a very important and interesting project with some potential exciting results. Okay, so now that we have kind of a background on the next generation Event Horizon Telescope, Einstein Telescope, and the Cosmic Explorer, I want to talk about some of the phenomena that third generation GWA is really going to be focusing on. And one really interesting thing that I've had a long time interest in, and I'm kind of trying to get more knowledge about, is the search for dark energy using gravitational wave astronomy. And in 1986, Bernard Schutz proposed that observations of gravitational waves from stellar mergers could be used to measure the distance redshift relation, especially if an electromagnetic counterpart were observed. And we'll talk in a minute about why that's important. But I'll just note again that Some of these new detectors are operating in conjunction with electromagnetic observatories, and this is important for this application. So as is well known, Daniel Holtz and Scott Hughes began to discuss this possibility as postdocs at Santa Barbara. And in 2005, they published a paper about one of the major challenges to cosmology for the foreseeable future, which is how to understand dark energy. I'll finish the quote, even though everybody knows this, the mysterious component responsible for the apparent accelerating expansion of our universe. So Holtz and Hughes, importantly, and sorry, I misspelled Daniel Holtz's name here. I added a T. One of the things that they started to speculate about was whether black holes could be used as standard sirens to complement what was already being supernovae, which were already being used as standard candles. So the important thing about supernovae is that their luminosity distance and redshift can be readily measured. And the dynamics are well known and so forth. And the distance redshift relation is one of the best observational probes of dark energy, and which of course maps the expansion history of the universe. But measurements of supernovae were not normally calibrated or checked against other sources, sort of independent sources of information about distance or redshift. Now, of course, the gold standard for checking measurements is to find an independent one, ideally one that uses an entirely different measurement process. And here I'm using the phrase measurement process in the way that Aaron Tal talks about it, that, when you measure luminosity distance or redshift, you're not just making a direct measurement, you're engaging in an entire process, setting standards, doing models, simulations, etc. If not only the measurement, but the phenomenon studied is different, then the cross-method comparison can be enlightening beyond just rederiving the measurement, right? So you're not just doing a calibration or a reduplication, you're actually getting kind of new information in a way by rederiving measurements. So for instance, black hole mergers and supernovae both allow for measurements of luminosity distance and redshift from the in-spiral of the black hole merger. But a binary merger has different parameters, at least in certain stages, and different sources of systematic error. And so especially the fact that about different sources of error is going to be important. So Holtz and Hughes began to consider how possible future observations of black hole and neutron star mergers could also probe the distance redshift relation. And as we all know, 11 years later after their paper, the first LIGO detection came. And following that, there have been many detections that showed black hole mergers as very effective standard sirens. So this is a quote from the 2005 paper. In this article, we discuss a completely independent standard candle, independent of supernovae, the gravitational wave-driven in-spiral of massive binary black holes. So since gravitational wave detections can be thought of as aural rather than optical, they're usually, of course, referred to as chirping signals. A more appropriate term for a gravitational wave standard candle is a standard siren. So because binary black hole systems are relatively simple and well modeled, at least in the in-spiral phase, the gravitational waves they generate determine the source's luminosity distance with high accuracy. So this is incredibly important. Luminosity distance is a very significant parameter, especially in the search for dark matter, dark energy. So for the redshift, they need the electromagnetic counterpart to remove sources of error. Now, this is where third generation, you might have been wondering where third generation gravitational wave astronomy comes in. So the planned space interferometer, the laser interferometer space antenna, or LISA, will be an instrument of much higher sensitivity, which will improve access to mergers. So binary black hole merger events will follow the mergers of galaxies and pregalactic structures at high redshift. The merger rate is poorly understood, but LISA is expected to measure at least several events over its mission, especially as it is sensitive to these waves to enormous distances. So already back in 2005, Holtz and Hughes were speculating about how a future space antenna might be able to pick up several events of binary black hole merger events that follow the mergers of galaxies, which of course would be incredibly indicative and interesting. So here, LISA is not the only third generation observatory investigating standard sirens. There are already, even now, even though these detectors haven't come online yet, there are already published papers about how Cosmic Explorer and the Einstein telescope will be used in the search for dark matter and dark energy. So Jin et al., the team led by Jin, there are two papers, 2022 and 2020, as well as others, are already engaged in forecasts of how the relevant parameters can be measured by Cosmic Explorer and the Einstein telescope, and how observations might be used to constrain the current models. So Holtz and Hughes note that detections of novel phenomena can cancel out sources of systematic error, which include calibration, model bias, and statistical methods. So supernovae have well-known systematic errors that could affect the measurements of distance and redshift. If the same measurement for luminosity, distance, and redshift is made, but with a binary black hole system that's not subject to those same systematic errors, that's a powerful corroboration of the supernova measurements. Now, of course, measurements of black hole binaries are subject to systematic errors as well. But in many ways, if there's agreement between the two measurements and the systematic errors are not considered to be the same, then even though you might not think that either of them is 100% accurate, you can still say that coming together on the measurements is still an even more powerful corroboration of the results. Let's put it that way. So this is another quote from this paper, which I'm mostly, again, quoting because it's kind of the standard source in this area. Gravitational lensing is going to limit the quality of binary black hole detections. Gravitational waves are lensed by matter exactly as electromagnetic waves are. And then this is the point that I just made, the binary black hole candle will have entirely different systematics from supernovae. And so concordance between the two types of measurement could alleviate concerns about evolutionary effects in supernovae and greatly increase one's confidence in all standard candles. So one of the interesting things about the new generation of gravitational wave detectors is just this incredible source of kind of confirmation and corroboration of results in the search for dark energy. But it's also the case, I should say, that this isn't the advances in third generation gravitational wave astronomy are not limited to just corroborating supernova measurements. So I've pointed out that, there's going to need to be a kind of comparison between the two sets of measurements, comparison between sources of systematic error, looking at the models, looking at the parameters that are measured. And that whole process is going to result in a ton of information about, for instance, methods of detection, methods of measurement, methods of modeling and simulation. And this is going to create, ideally, but I think reasonably enough, this sort of process usually creates a great deal of information and progress around processes of measurement, instrumentation, modeling, and simulation. And this isn't, again, this kind of thing is not limited, and I don't want to sound like a broken record, but it's not limited to just increasing the sensitivity of the detector, right? This is much more, a much sort of deeper set of methods and inferences that are being made. Okay, so in this next part of the talk, so that was kind of a like a golden oldie of 2005, which, believe it or not, was 20 years ago. But now what I want to do is talk about some of the new detections, new phenomena that could be also found. And I want to talk about potential synergy between results and methods of these new detectors and existing results and methods. And I kind of want to bring the word synergy back because I think it's been kind of much, it's been harmed by being associated quite so much with sort of business speak or corporate speak. But I think it's a really important point that sometimes what happens is you have science that's going on over here and science that's going on over there, kind of a little bit like we were just talking about with supernova and binary black hole merger measurements of distance and redshift. When you bring them together, you kind of get you get more out of the comparison of the methods and measurements than you brought in. And I think that one thing that's incredibly important about new detectors, new methods, and sort of new instrumentation is that you often get kind of more progress than you thought you might, because in fact, what happens is you're able to, with the new detections, you're able to update a lot of your parameter estimates, your models, your instrumentation methods, like questions that you had for a long time are going to be answered and so forth. So I want to talk about some of and of course that's in the ideal case, but I want to talk about some of the cases in which, if we're being optimistic, some of the things that might be exciting about the third generation. So one of them is this incredibly important phenomenon of tidal disruption events. So there's a whole group of people. I mean, if you go to the Black Hole Initiative, there's a whole group of people working on accretion phenomena. But the phenomenon of tidal disruption is incredibly important and gives us a lot of access to a lot of information. So this is from NASA, both the image and the quote. Every galaxy has a black hole at its center. Usually they're quiet without gas accretions, but if a star creeps too close to the black hole, the gravitational tides can rip away the star's gaseous matter. Interactions and mergers between stars, neutron stars, and black holes are among the most likely detections in third-generation gravitational wave astronomy. These are expected. The new detectors can work with improved templates, models, and simulations to distinguish between stars, black holes, and background signal. And here, for the next few pages, I'm going to go off of a report from the Max Planck Institute that is reporting from a recent paper by Brown, Capano, and Krishnan called Using Gravitational Waves to Distinguish Between Neutron Stars and Black Holes in Compact Binary Mergers. And so this is from a fairly recent paper, 2022, in the Astrophysical Journal. So to be clear, for ease of presentation, what I've done is basically screenshot from the MPI kind of report on this paper. So this made it kind of easier to access. So the question that's at issue here is what is needed to distinguish between binary black hole and neutron star black hole mergers. So one of the questions that's really important in recent gravitational wave astronomy is when there's a gravitational wave from a low mass merger, but without a concurrent electromagnetic signal, how can you distinguish a lightweight, low mass binary black hole merger from a neutron star black hole merger? And so recently, there have been researchers at the MPI, Leibniz University Hannover, and at Radboud University, and they've used a simulated search for gravitational wave signals of this kind to answer the question. And this is the paper that was published in the Astrophysical Journal. And then this is what's important for this talk. Third generation detectors such as Cosmic Explorer and the Einstein telescope will be able to make a clear-cut distinction under favorable circumstances. So this is kind of one of the things that really is motivating this third generation. And this paper is showing how if with improved models, templates, methods, etc., that it will be possible under the right kinds of circumstances for these new detectors to tell these types of mergers apart, which has been in the past a difficult thing to discriminate. So here, this is me sort of interpreting what the authors say here. They note that new instruments are needed, the Cosmic Explorer and the Einstein telescope, but even judging that new instruments are needed required a simulated search for gravitational wave signals and the relevant models. So knowing how the new and more sensitive instruments will be put to use requires reasoning using models and simulated events. Oh, sorry. So this is just going into slightly more detail about exactly what the problem is. And this on the right is a simulation of a neutron star black hole coalescence in which the neutron star is tidally disrupted. So this is the tidal disruption event that I mentioned earlier. So this is from the MPI's website. Some types of signals can be harder to tell apart than others. So it can be almost impossible to distinguish a binary black hole merger where one black hole is very small from a neutron star black hole merger. So this is a quote from Stephanie Brown, who's at the MPI and at Leibniz. So this is something that, if you were listening carefully, came up a bit earlier. When, if you remember, one of the advantages of these new detectors is that they can say much more about the density of matter inside a neutron star. So there's much more information available to the new detectors about this. And it turns out that the way to, it's kind of obvious when you think about it, but it's a really interesting and exciting point. Neutron stars, unlike black holes, consist of matter. Here I'm again reading from the site. So there's two ways in which the presence of a neutron star can be determined. The presence of an electromagnetic counterpart, or the imprint of matter effects on the gravitational wave itself. So, and as you can imagine, in order to detect the latter, it's going to take a very, very sensitive detector. So this is actually, again, this is their website. Third generation detectors are required. And so on the right here, you see this beautiful artist's impression. I really recommend actually looking up this article. It's very cool and pretty short. There's an artist's impression of the underground Einstein telescope, which is the planned third generation detector. So the results of the paper are that only when the black hole was relatively lightweight was there a chance of clearly observing tidal effects. And that's because the tidal effects are stronger if the black hole's mass is more similar to the neutron star mass. So even at design sensitivity, the current detector network can't distinguish between those two different types of signals. But only Cosmic Explorer would be able to tell these two types of signals apart. So to distinguish between a binary black hole merger and a black hole neutron star merger with these interesting tidal effects, tidal disruption effects that people want to investigate and study. So this is one really cool thing that the next generation of detectors can potentially have access to. In keeping with my overall point, I just want to point out that on the one hand, it is absolutely true that the new detector sensitivity is very important in order to be able to get to this result. But it's obviously also true, it's obviously also true that there's a great deal of modeling and simulation and judgment and inference that's going into the question of being able to distinguish between these different types of phenomena and being able to establish it with certainty that there's, one or the other type of system present. Okay, so I just want to close, because I know I do need to close, with a few words about this recent paper, Eng et al., in Physical Review D, called Multi-Band Gravitational Wave Searches for Ultralight Bosons. And this is a really, really cool phenomenon called multi-banding, which is I really like. It sounds like you should be getting together, with a bunch of different garage bands or something, but it doesn't mean that. So let me just read from the paper. Gravitational waves may be one of the few direct observables produced by ultralight bosons, conjectured dark matter candidates that could be the key to several. So we've moved from dark energy to dark matter. That could be the key to several problems in particle theory, high energy physics, and cosmology. These axion-like particles could spontaneously form clouds around black holes, leading to continuous gravitational waves that could theoretically be detected by instruments on the ground and in space. But what's cool about multibanding is that both types of detector, space-based detectors and ground-based detectors, could be used in tandem to detect these clouds of ultralight bosons. So this is multibanding. So the idea is you'd have a space-based detector, you'd have a ground-based detector, and they'd kind of tag team to pick up the signals from these clouds. And so the LISA space mission will provide crucial information that will enable future ground-based detectors like Cosmic Explorer, the Einstein telescope, to search for signals from boson clouds. So the idea is the LISA telescope will get information that allows the scientists running Cosmic Explorer and the Einstein telescope to kind of narrow the search and figure out how to search for signals from boson clouds around these individual black holes and where in the sky to look and so forth. So again, I just want to point out that this is something that goes well beyond just saying, well, we're going to have this amazingly sensitive detector. The detector will be very sensitive, but what's cool about multibanding is that there's this, again, synergy between different methods and different instruments that's going to result in kind of more information and the ability to kind of identify the right kind of event to zero in on in order to detect clouds of ultralight bosons, which is going to be potentially a really interesting set of results, not just in gravitational wave astronomy, but also in particle physics and the search for dark matter. So this is something that I think goes well beyond, of course, it employs the improved detector sensitivity, but it goes well beyond just improved sensitivity. So this is my main point. So just to sum up, there are two general sources of novel results in third generation gravitational wave astronomy. One is obviously detector sensitivity, a new range of sensitivity. The press releases talk about, going where we've never gone before and, exploring the full range of cosmology and so forth. And that's absolutely true. But the second is, again, to revive this word, synergy with new models, simulations, methods, constraints, and so forth, including increased discrimination between types of events, neutron star and black hole mergers, and collaborative detections, including multibanding that uses different types of instruments. So I think these are particularly interesting and important results that could ideally be achieved by the next generation of gravitational wave astronomy. So thank you.
Thank you very much, Lydia. So we can open our discussion right now. I've read before that Julius wanted to add something on the next generation Event Horizon Telescope. Is it correct, Julius?
Hey,
Okay.
sorry. No,
Yeah.
sorry.
Yeah.
No. I don't have like. First of all, thank you very much to Lydia for a shout out, and it's just an offer if anyone is particularly interested in this. But I think this would take us too far away from the focus of Lydia's talk, and I think we should focus on that first. But if anyone's interested in the EHT related things, which are not um, which are not gravitational waves, right? It's like high frequency interferometry. So the messenger that one was working with is very different. But there's a lot of exciting developments on that front. And if anyone's interested, I'll be happy to talk about. But I think we should first focus on Lydia's talk, maybe.
Thanks.
Okay, so thank you. Okay, so are there questions? You can raise your hand through the chat. I can Julius again, Marco. Yeah.
Yes. So obviously I actually had an agenda in kind of throwing this off myself. And so yeah, thank you very much, Lydia. This is for an amazing overview of this third generation detectors. I have I have one super minor terminological question in that, and then the second one is kind of much more interesting. So in this preprint from the Albert Einstein Institute folks, which you showed, they use the phrase, I think, LIGO Voyager. Is this the same as LISA, or do you know off the top of your head? If
From
not,
the
then don't worry,
Einstein,
I'll
this
just
one?
check.
Was it this
Uh,
one?
it was at this point where they were making the. mm,
No, that can't be it.
no, it was at some other slide.
Oh, sorry.
Um,
So they use the
God.
phrase advanced LIGO?
There was this was this paper from the Albert Einstein Institute folks from I think 2022.
Oh, okay. That was
They were
much later.
making
Okay.
this point that like only I think the Cosmic Explorer or the Einstein Telescope, I
Yeah, this one.
think
Is that right?
No, that's also not this one.
It's also
Please
not this one. Sorry.
forward.
Sorry.
Sorry.
So what was the relevant?
The phrase they used was LIGO Explorer, and I
Oh,
was just not sure what that referred to. If that meant like, if that was the way of
yeah.
like referring to Lisa, or that I'm not familiar with,
That
or
may be Lisa, or it may have been a mistyping of Cosmic Explorer. It seems like that might have been more.
maybe.
Yeah, I'll
Well,
look
maybe
into it, but yeah.
okay. I'll just check directly with the paper. Okay,
Okay.
but okay. So let's move to the more interesting question. So,
Yes.
um, uh, you made this point throughout your talk that like um, there is a lot of um, sort of interplay between theory and observation, and of course we could see it along around Thales or around sorry in accordance with Aaron Thales' work or in accordance with George Smith's work. But I'm curious if you know, like if there is something, I don't know how to phrase it exactly, but like if there are like big sort of changes in the theoretical or numerical background for the third generation detectors with respect to, let's say, like Virgo Cagra. And yeah, and
Yeah.
if so, like, do you think that the sort of like philosophy of science, kind of like discussions or landscape of these, like, how should that be influenced if there is any kind of like deep change in the theory or modeling?
Right.
I know it's a very
Right.
big question, but I'm just curious about your thoughts.
I was going to say that is a fantastic and very big question. Um, and I think I mean so the first thing that I would say is that in some ways part of what I'm pointing out is that uh this would be a really interesting focus for philosophy of science because I think that there are a couple of things that happen that make these advances. So notice that I'm not going to answer your question about whether there is a big change because I don't know. But I think that one of the things that's really important is the change in, for instance, the computer models has been profound, right? So um, one of the things that I think is really important about the work of Aaron Tall, Wendy Parker, Eric Winsberg, and others on these questions is that methods of simulation, Johannes Leonhard, I should mention, methods of simulation become important for these kinds of combinations of methods and being able to derive results from novel instruments. And I think that one of the things that happens that's really important that philosophers of science would be, I think, fascinated in if we focus on it is there are kind of theoretical implications to the changes in simulation methods, to the changes in the computer programs. Um, and I think that, for one thing, I think there's kind of this thought that, well, this is just logic, right? These are just computer programs that are just making logical inferences, and there aren't kind of substantive points being brought in. But I think that, for instance, just to take something extremely simple that was in the talk, um, being able to distinguish between um, two different types of merger that you couldn't distinguish between before is an ontological point, right? There's two different types of system that you can talk about that you couldn't talk about before. And you at the very least have to have a kind of concept for each and ways of standardly measuring them and all of that kind of thing. And so I think that that's at least something that if we have novel detections of a new type of thing, um, there's a kind of scientific ontology point that can be made that, we have to change our concepts, we have to update our models in that sense. I realize that that's a kind of seemingly minor point if you're trying to make the claim that there's a kind of interplay between theory and observation here. But I think that you start there and you talk about Having said that, I'm not going to backpedal that far. Um, it's it's also true that in many cases, being able to measure a parameter precisely can have incredibly important theoretical ramifications, right? So many of the parameters of binary black hole systems are sort of indirect confirmations of GR as opposed to the Newtonian, and so and that confirmation comes from the ability to measure like the orbital frequency of a system with great precision, right? It's exactly that precision that gives us the test of the theory. And so I do think that this progress could potentially not only give us kind of new, um, yeah, but having said that, having said all of that, do I know of some particular way in which the third generation um, detectors depart substantially from advanced LIGO? I don't. I would love to know if there is something. I think that would be really cool. Thanks,
Okay.
Julie.
Thanks a lot for the question and the answer. And Marco,
Yes. Can you hear me right?
Yes.
Okay, perfect. Thank you very much for the talk. So I have like perhaps related, like a question related to these last comments that you made about like, oh, the importance of measuring parameters for like new parameters with greater precisions in order to verify or dispute like certain theoretical assumptions in our theories, in a sense.
Right.
And so this is probably a little bit of taking it from afar, but at certain point you mentioned how, for example, we can use standard sirens as new standard candles in a way to measure distances with astronomical and cosmological objects. So like the example was comparing them to supernovae type 1a, where you say, I think what you said is that, well, we would have like a different autonomous method for measuring distance. Then we can cross-check in a way the systematics for these two different methods and have like a better distance measurement of those objects. But and here's perhaps a silly question, maybe. But one of the problems with, like, for example, like distant supernovae type 1a is not. It doesn't seem to be, at least to me, the models and the theoretical background for that measurement. The theory onto which we base those measurements is fairly solid. The problem is that we have like a small pool from which we gather distances. So like the systematics are quite high because we measure only like 10 objects. This is a made up number, obviously, instead of thousands, so that the systematics would go down. So having new methods, new autonomous methods, first of all, I don't know how many data points we would have with these new methods, doesn't necessarily warrant a more precise distance measurement as compared to standard candles like supernovae type 1a because of cross systematics. We might just have very large error bars for these new methods, which would give us not very much of an information with respect to those distances. Does it make sense? So isn't that a risk, maybe?
Yes. So this was a very perhaps untimely, in a way, triumphalist approach to like what I was presenting was kind of like, if ideally this
Okay.
is what people are hoping for from these new detectors. Um, I think that the goal, um, I think that perhaps the way that the standard siren approach would be explained is slightly different. So the idea, and so this maybe explaining it in this slightly different way would resolve the issue or the risk, and maybe it wouldn't. I'm inclined to agree with you that there is a risk. So first I'll say why I'm inclined to agree with you and get you on my side, and then we'll talk about the other thing. But I agree with you because I think that there is actually what Franz Pretorius and Eunice, his sorry, I can't remember his collaborator's first name, but Eunice and Pretorius have pointed out that there's a theoretical bias in the measurement of luminosity distance in the gravitational wave templates, right? So like there are various sources of, and I did mention that there are various sources of systematic error, not just gravitational lensing, but also kind of modeling error and so forth in the case of binary black hole detections. And I think that there obviously are, again, there are well-known systematics in the case of type 1 supernovae. And so I think what's happening is that people are saying, look, Holtz and Hughes especially have said this. I think there are well-known systematics in both cases. And so if the measurements agree, that's a kind of brute, coarse-grained, it's not a confirmation and it doesn't give us increased precision. The last thing it gives us is increased precision of measurement, but it gives us a kind of very broad, coarse-grained reassurance that we're on the right track.
It will be encouraging, at least
It's
encouraging.
encouraging. We didn't derive different measurements. And that would have been discouraging, right? So I think that's the idea, is like, it's not confirmation, it's nowhere near confirmation, it's not increased accuracy or precision, either one. It's just, it's good rather than bad, right? I think is the idea, right?
And this leads me to my second point, where I think
Right.
the study was different with respect to, like, for example, high energy particle physics, where like there was a
Yeah.
large discussion on whether, for example, the background noise was a possible cause for was the possible source for new physics that was undetected, and then like physicists discussed about the fact that no, the background noise is extremely well tested in that respect, and so like it's very unlikely that new physics is hiding there. We just test for new jets or new particles interactions. So like their new experiments or the measure of new parameters or the measure of a parameter with higher precision kind of gives them the assurance that that is a parameter measured with higher precision. While here in cosmology with these third generations, like, since the measurement of a parameter, yes, is done by using better detectors, but also comes with new models, new measuring processes. Like, can we be sure that the precision will be higher for these new measurements, and not just better precision but with higher systematic errors, for example, because of the new methods, the new models, and new theoretical models that we bring about when measuring those new parameters, or whenever measuring those parameters with these new methods. Sorry.
Right. Well, that's a great point, because I think that's exactly the meat of what's going on there, right? Is that I think that you can say something a little deeper than just these measurements correspond, right? They seem to be within the same error bars or something like that. You can say, look, it's really interesting that this was an independent process. And that seems, again, in the way we've just discussed, to be encouraging. But if the systematic errors in the case of third generation GWA are so high, the gravitational lensing, then it seems like, well, that doesn't really give us new precision in the measurements. It doesn't give us anything new. Having said that, and I haven't gone through this, and so I can't speak with any authority about it. Not that I've done any of that today, but I have heard that if there's an electromagnetic counterpart, that does remove some of the sources of error. And so this is one of the reasons why it's so important that these detectors are operating in tandem with electromagnetic detectors, so that there's this kind of third source of corroboration. This is also where I think the NGEHT comes in too, is that if you then have a kind of potentially, maybe not now, but sometime further in the future. But I won't. Again, I can't speak on that with any like in an informed way. But I think the issue then becomes, what is the information that's desired? Is the information more precise measurements, or is the information that's desired like where to look for measure, for luminosity, redshift relation, right? Like which sorts of systems should we look for? What kinds of measurements will be most salient, right? What's the merger rate? What's the what kind of um, systems are we looking for? And I think one question to kind of step back and ask is, well, what stage are we at here? Like, are we at the stage of sort of narrowing things down in order to then try to build and, um, in order to know what to look for the next stage, right, at some time in the future? And I think it's possible that that's kind of the lesson here, is to have some humility about like where we are in the search for standard candles and standard sirens, and think, okay, we're actually fairly early on in the search, and what we're doing right now is kind of crudely, that may not be the right word, but broadly narrowing down like where to look for the next set of phenomena and methods.
Thank you.
Thank you.
Thanks a lot, Marco. Thank you, Lydia. Of course, these are, I think, very important questions, and I don't know whether there are the comments from Laura Federico. I also see Gauvin is online. Are there questions, comments? No? Okay, so if not, then I thank our speaker again. Thanks a lot, Lydia, for this talk, and hope to see you all soon for another meeting.
Thank you.
Thank you. Thanks a lot.
Thanks very much, everyone. It was a great discussion. Talk to you later.
Thank you.
Bye bye. Thank you.
Bye.
Bye. Bye.